The use of components made from lightweight aluminum depends on the ability of aluminum to alloy or mix with other elements, causing the resulting alloy to significantly increase in strength and hardness. Aluminum alloys are composed of approximately 90 to 95% aluminum, with the remainder being other elements, such as copper, zinc, magnesium, manganese, and silicon. When mixed with the aluminum, many alloying elements make the resulting alloy heat-treatable, and thus strong enough for use in many aerospace, automotive, and commercial applications. To fully understand the significance of an aluminum heat treating operation, a knowledgeable heat treater must first completely understand the alloy and heat treat designation system that is used to identify the type of alloy that is being processed and the temper to which it is being heat treated. A typical alloy and temper designation for a wrought high-strength aluminum alloy is shown here, 7075 T6. All wrought alloys, that is sheet, plate, forgings, and extrusions, use a basic four-number code system that identifies a specific alloy. The first four numbers identify the alloy type. In this case, the alloy is known as 7075. The second part of the designation, T6, identifies the temper to which the alloy has been heat treated. Not all aluminum alloys can be strengthened or hardened by heat treatment. The different types of aluminum alloys can be broken up into two groups. The first group consists of alloys that can be hardened by heat treatment. This group includes the 2000 series, which are alloys of aluminum and copper, the 6000 series, which are alloys of aluminum, silicon, and magnesium, and the 7000 series, which are alloys of aluminum, zinc, and magnesium. Most of the heat-treatable aluminum alloys fall into these categories. The second group are alloys that cannot be hardened by heat treatment. These are the 1000 series, which are mainly pure aluminum alloys which have no major hardening element, the 3000 series, which are alloys of aluminum and manganese, the 4000 series, which is a series of aluminum and silicon, the 5000 series, which is a series of aluminum and magnesium, and the 8000 series, which includes mostly miscellaneous alloys. Alloys from these series are not hardened by heat treatment. They are used in the softened condition or are strengthened by cold working operations. They sometimes may be annealed or stress relieved by thermal processes. Many casting alloys are heat treatable. Casting alloys use a 3-digit identification system, modified by letters or decimal point extensions to explain slight differences, such as 356.1, although it is common practice just to use the first 3 digits to identify the alloy. The most common heat-treatable casting alloys are the 300 series alloys, such as 356 T6, and the 200 series alloys, such as 201 T6. When an aluminum alloy is heat-treated, the final heat-treated condition of that alloy is identified by a temper designation system. The temper designation system for heat-treatable aluminum alloys involves the use of the letter T followed by a number or series of numbers. The T means temper and indicates that the material has been heat-treated to a hardened condition in some manner. The alloy with its appropriate T designation then takes a form such as this: 2024 T351, or 7075 T652, or 356 T6. The location of each number following the T is usually termed a digit, that is, the first digit, the third digit, and so on. There can be as many digits as necessary to fully describe the particular temper of the alloy. The digit can be any number from 0 to 9. For our discussion, we will call an unidentified digit X, so that in the general form, the alloy and temper would appear as 7075 TXXX. In this case, there are 3 X's or digits following the T. Each number properly placed in a digit location indicates that a distinct operation has been performed on the alloy to achieve that temper. The first digit identifies the basic temper of the alloy. There are 10 basic digits which have been specified by the Aluminum Association. Some tempers are commonplace in the heat treat shop, and some are rarely observed. Experience has shown that to achieve a clear understanding, it is best to group the basic temper designation into categories containing similar tempers, and to make direct comparisons between the similarities and differences between these tempers. The differences between the similar tempers of the more common designations will be described later. T3 and T4 are alike in that they both are solution heat treated, quenched, and naturally aged to achieve the required properties. T6, T7, and T8 are alike in that they are all solution heat treated, quenched, and artificially aged to achieve the required properties. T1, T2, T5, and T10 are less common tempers because they are not solution heat treated. They all represent material that has been rapidly cooled after some fabrication process and then aged. The differences between them are as follows. The T1 temper is naturally aged. The T5 temper is artificially aged. T5 is used mostly for extrusions and castings. The T2 temper is cold worked and naturally aged. Previously, it was used as a designation for an annealed condition for cast products, but now is rarely used. The T10 temper is cold worked and then artificially aged. The T9 temper is cold worked after solution heat treating, quenching, and artificially aging. It applies to products such as wire, where the cold work after aging improves the strength. Let us now review the differences between similar tempers. The difference between the T3 and T4 tempers is that the T3 temper uses a slight amount of prescribed cold work specifically for the purpose of improving strength. This cold work is performed after solution heat treating to improve the mechanical properties. The working operation is usually performed by stretching or rolling and is normally accomplished at the primary mill. Thus, the T3 temper is rarely produced by the commercial heat treater. The T4 temper may or may not be flattened or straightened. In the case of T4, the straightening operation is performed with the objective of achieving a specific dimensional tolerance and not for the purpose of improving properties. The T3 and T4 tempers are both naturally aged. They harden naturally at room temperature in approximately 4 days after solution heat treating and quenching. The hardening reactions occurring at room temperature cause a significant increase in strength and hardness. The T6, T7, and T8 tempers require artificial aging in an oven or furnace in order to achieve the required level of properties. The differences between the T6, T7, and T8 tempers are as follows. The T6 temper requires furnace or oven aging using appropriate times and temperatures so that without cold work, the highest possible level of tensile properties is obtained. In the case of some alloys, such as some commercial castings, the material may be underaged in order to retain a usable level of ductility. For wrought alloys, in most cases, the T6 temper usually represents the highest strength possible for a given alloy. The T7 temper involves artificially aging to achieve some special characteristics at the sacrifice of strength. In most cases, the objective of the T7 temper is to improve the stress corrosion or exfoliation corrosion characteristics of the 2000 and 7000 series alloys. T7 tempers are also used to achieve improved dimensional stability. These characteristics are accomplished by overaging. That is, aging is conducted at a higher temperature than that which is used for the maximum strength T6 temper. The T8 temper involves the use of a cold working process similar to the T3 temper to improve the mechanical properties. The T8 temper is artificially aged after the straightening operation. T3 tempers are normally converted to T8 tempers by an appropriate furnace or oven age after the cold working operation. Let us now discuss the secondary digits that are used after the basic temper digit. The digits used after the basic temper digit are termed the descriptors, for they describe some specific operation that the material has undergone in the heat treatment process to achieve a specific purpose. The descriptor digits are numbers that are added after the basic temper or first digit. Examples are the 1 added to the T6 to make T61, or a 51 or 52 added to the T6 to make T651 or T652. Let's review the function of some of the more common descriptor digits to explain their purpose so that the differences between tempers, such as T61, T42, T652, and T7352, can be easily understood. Typical uses of a descriptor digit would be to indicate that a different quench water temperature had been used, to note that a stress relieving operation has been performed, or that the material has been processed in a special manner in order to achieve special properties. The user-defined descriptor 1 takes the common form of TX1 or TX11, such as T61 and T611, or T31 and T81. The T61 and T611 tempers are frequently encountered in commercial heat treat plants, for they often designate material which has a quenching modification. An example is the alloy 2014 T6 and 2014 T61 tempers used in forgings. 2014 T6 is cold water quenched, and 2014 T61 is boiling water quenched in order to achieve greater dimensional stability. When one is used with T3 or T8, as in T31 or T81, it identifies a specific level of cold work, usually 1 1/2 to 3%. For castings which are heat treated and use the T61 designation, it usually refers to an aging modification rather than a quenching or cold work modification. The user-defined descriptor 2 takes the common form of TX2, such as T42 and T62. These tempers are frequently encountered in commercial heat treat plants, for they designate material which is heat treated in a user plant or commercial facility, in contrast to that which is heat treated at a primary or producer mill. In many cases, material heat treated to a T4 temper will require a higher level of tensile properties than material heat treated to a T42 temper. The next most important designations to recognize in aluminum alloys are the stress relieved tempers. When stress relieving of heat-treated aluminum alloys is required, they are normally stress relieved shortly after quenching from solution heat treatment. The stress relieving process is either by cold working or by a thermomechanical or uphill quenching procedure. Thermal stress relieving techniques, which are widely used to stress relieve steel alloys, are not particularly effective for aluminum alloys, although they are sometimes applied after severe fabrication operations. We will describe more of thermal stress relieving later in this video. The descriptor digit 5 is used to indicate that the material has been stress relieved after solution heat treating. A second descriptor is used to specify the type of stress relief used. So the nomenclature would take the form of TX5X or TXX5X. The secondary digits normally used in this case are the following: 1. Stress relief by stretching. 2. Stress relief by compression. 3. Stress relief by miscellaneous thermal or thermomechanical treatment. And 4. A special compressive treatment for die forgings where the finish forging die is used for the compressive treatment. Stress relief by stretching is normally applied to long parts, such as plate and extrusion products, and in some instances to ring forgings that lend themselves to stretching. Compressive stretch relief is used on complex shapes where stretching is not possible and is most applicable to both hand and die forgings and sometimes rolled rings. The typical appearance of stress-relieved tempers would be the following: 7075 T651, alloy 7075 in a T6 temper, where the product is stress relieved after quenching by stretching. This temper is usually applicable to sheet and plate products and sometimes extrusions. 2014 T652, alloy 2014 in a T6 temper that has been stress relieved after quenching by compression. 7050 T7354, alloy 7050 in the T73 temper. The part is a die forging that has been compression stress relieved after quenching in the finish forging dies. For some product forms, when stretcher stress relieving, such as denoted by TX51, is applied, an additional descriptor digit is used to indicate the amount of the stretch. Examples include 7075 T6510, stretched 1 to 3% with no straightening allowed, and 2024 T6511, stretched 1 to 3% with minor straightening allowed. When using the stress relief nomenclature, the 5XX or 5XXX series of numbers is always positioned at the end of the respective temper it represents. For example, T73511, T4251, T652. The alloy and temper designations that we have just reviewed are the most common ones used in the aluminum heat treat plant, but there are many others. In some instances, there have been cases where a temper designation might have a specific meaning to one company and could mean something completely different to another. If this situation occurs, it is best to be sure that a correct interpretation is obtained from the organization requesting the work. In the case where more complicated designations need to be determined, the heat treater must precisely determine from the customer exactly what process is to be used to achieve that temper. In addition to T designations that identify the final heat-treated condition, there are other temper designations that the heat treater must recognize. These are designations that are used for interim processing operations prior to the final hardening treatment. Prior to the heat treatment, the material is usually received at the heat treat plant in a non-hardened condition. These are as follows. F, the temper used to designate material in the as-fabricated condition, usually from the producing mill, such as forged, as extruded, and so forth. O, the O designation represents the fully annealed or softened condition. Material is placed in the annealed condition so that it can be further formed or fabricated in some manner, or to relieve stresses placed in the material by some fabrication process. O1 is a special formability anneal used for machining applications. In addition, there are two other tempers commonly used for identifying interim conditions in the heat treat plant. These are AQ, the temper formed immediately after quenching before any appreciable natural aging occurs. At room temperature, this temper lasts for about a half hour. Refrigeration at temperatures to 0 degrees Fahrenheit or lower can preserve this temper for up to many months. W, unstable temper, that is formed during the natural aging process. This temper exists as soon as significant aging starts after quenching and remains until no further natural aging continues. When those tempers are used, they appear as 7075O, 2014F, 7049W, 2219AQ, and 7050O1. The solution heat treating operation is the first step of the hardening or strengthening process for aluminum alloys. The solution heat treating operation is basically a conditioning process, the purpose of which is to condition the alloy for a later hardening or precipitation operation, which we will discuss later. Aluminum alloys are made by adding elements to a molten charge in a foundry. When this cast material is cooled in the mold, the alloying elements segregate to unfavorable locations in the structure, mostly in the grain boundaries. When this alloy is later heated, the alloying elements tend to move to favorable locations in the structure, creating a homogeneous material. This movement of the alloying elements to locations within the aluminum structure is termed dissolving in a solid solution. During the solution heat treating process, we attempt to dissolve in solid solution the maximum amount of the hardening atoms, such as copper, zinc, magnesium, or silicon. As we shall see later, the more solute atoms that can be dissolved during the solution heat treating operation, the higher the final properties that will be achieved. Let us now look at the importance of the solution heat treating temperature. The rate at which the hardening elements dissolve in aluminum alloys in the solid state increases greatly with increasing temperature. For instance, very little copper will dissolve in the aluminum in the solid state at room temperature, while at 900 degrees, approximately 5.6% copper will dissolve. The final tensile and yield strengths of heat-treatable aluminum alloys are directly dependent upon the amount of hardening atoms that are dissolved before quenching. Most high-strength 2000 and 7000 series aluminum alloys show the highest level of properties at the highest solution heat treat temperature. This graph shows the effect of the solution heat treating temperature on the tensile properties of 2014 T4 and 2014 T6 sheet material. The maximum strengths occur just below the eutectic melting temperature of 955 degrees. Most high-strength 2000 and 7000 series heat-treatable aluminum alloys behave in a similar manner. As we have observed for most heat-treatable aluminum alloys, the maximum amount that can be dissolved occurs just below the eutectic temperature. The eutectic temperature is that temperature at which actual melting of certain particles starts to occur when the part is reheated for any reason. Thus, in order to achieve the best properties, it is often necessary to perform the solution heat treat operation at the highest possible temperature just short of melting. This operation is very critical for most high-strength alloys, such as 2014, 2024, 7075, and 7050. Since the nominal temperatures specified for commercial solution heat treating of these alloys are only 10 to 15 degrees below the eutectic melting temperature, good furnace control and uniformity of temperature within furnaces and operator understanding of the heat treat process are essential. We will discuss the problems of eutectic melting shortly. For some lower strength alloys, such as 6061, maximum strengths are achieved at a solution heat treating temperature which is significantly below the onset of melting. The effect of the solution heat treating temperature on alloy 6061 is shown in the table. The maximum properties occur at 1000 to 1025 degrees, while the eutectic temperature is not reached until 1080 degrees. Heat treating at a temperature above 1025 degrees actually results in a slight decrease in properties. All of the solute that will dissolve into solid solution has dissolved by the time the temperature has reached 1025 degrees. Thus, increasing the temperature above that has little effect, and as a result, this alloy is normally solution heat treated at 980 to 1010 degrees, well below the eutectic melting temperature. The control of the time interval at temperature is also an important consideration if acceptable strength and hardness is to be achieved. Sufficient time must be employed during solution heat treating to allow all the solute atoms to dissolve and diffuse evenly so that the resultant structure is homogeneous. The actual soak time needed at the solution heat treating temperature depends upon the type of furnace used, type of product, castings, forgings, sheet, and so forth, working history, and the thickness of the part involved. The recommended soaking times for air furnaces and salt baths are shown here for wrought products. The primary requirement for soak time for wrought or worked alloys is the thickness of the material being heat treated. Thick section wrought products, such as plate and forgings, are generally heated at least 1.5 hours per inch of thickness. Much shorter times, 10 to 30 minutes, are adequate for sheet products. Special considerations apply in certain instances. There is no firm rule as to the length of time that a particular part needs to be soaked because of its product form. Forgings that are produced directly from billet stock may need longer soak times for adequate solution heat treatment than those produced from pre-extruded stock. On the other hand, small no-draft forgings, especially those that are produced from extruded stock, can be soaked for much shorter periods of time. Castings are usually soaked for longer periods of time in order to homogenize the cast structure. Sand castings are usually held at the solution temperature for about 6 to 12 hours. Permanent mold castings, if they are chilled correctly, sometimes can be soaked for shorter periods. Castings that are produced from using high chill rates normally result in a finer dendrite cell size, and good properties can be achieved with shorter soak times. Longer times may be necessary if premium properties are required, if chill rates produced in the casting process are slower, such as investment or plaster castings, or if marginal chemistries are present. For most aluminum products, there is a minimum time required to achieve full solid solution condition. As long as the furnace atmosphere and environment are properly maintained and the maximum temperature is not exceeded, there is no need to restrict the maximum furnace time or the number of times that a material may be solution heat treated. In the case of alclad materials, however, excessive soaking can cause the cladding to diffuse within the base metal, and eventually the cladding and the resulting corrosion protection will be lost. To avoid this diffusion, the time of solution heat treatment for clad sheet products must be limited to only that duration needed to achieve the specified mechanical properties. An illustration of the effects of alclad diffusion is shown here. A sample of 7075 T6 sheet, which had been solution heat treated for an extensive length of time, is shown. Suggested maximum solution heat treat soaking times for sheet alloys are shown in this table. Alclad products of the 2000 and 7000 series alloys are normally not re-solution heat treated more than the number of times specified in the next table. One additional reheat treatment is permitted beyond the limits of the table if the heating rate is sufficiently rapid, such as salt bath heating, so that the material will satisfactorily pass an intergranular corrosion test. Eutectic melting during solution heat treatment must be avoided at all cost. It is the most important consideration in the heat treatment of aluminum alloys. When this temperature is exceeded, intergranular networks of a brittle glass-like eutectic are formed. If extensive, this network may significantly decrease both the strength and ductility of the part. In addition, quench cracking is sometimes encountered when the normal solution temperature is exceeded. The eutectic that forms in the grain boundaries can severely damage the material such that the parts will show no measurable ductility. In one instance, a cast aluminum automobile wheel, which had exceeded the eutectic temperature, actually shattered into about 20 pieces when it was accidentally dropped after quenching. The problem of eutectic melting is extremely serious because of two main reasons. One, it is a condition that cannot be salvaged by subsequent reheatment. Once the condition has been created by careless solution heat treatment, the only recourse in most instances is to scrap the material. Two, it is nearly impossible to detect the condition by normal non-destructive testing techniques. Material that has been overheated may achieve a normal hardness after aging, and the effect on electrical conductivity readings is very small. Thus, an inspector may not discover an overheated defective part. Only destructive testing will reveal the condition. If the overheat condition is extensive, tensile tests will show low ductility and sometimes low tensile and yield strengths. An example of an overheated 2024 part is shown in this photomicrograph. The damaged part exhibited an extensive rosette pattern and grain boundary melting in the microstructure. The published eutectic melting temperatures, as well as the normal solution heat treating temperatures, are shown here. it can be seen that the solution heat treating temperatures are extremely close to the melting temperatures of most 2000 and 7000 series alloys. Nothing can be more discouraging to an aluminum heat treater than to find that a load of the customer's expensive, fully machined parts are heavily blistered after a solution heat treating operation. These blisters are tiny bubble-like protrusions which appear on the aluminum surface. Blisters can also be an indicator of an inferior structural part if the condition is found to exist below the part surface. Blisters are part of a phenomenon of aluminum alloys that is erroneously termed high-temperature oxidation, or more commonly HTO. High-temperature oxidation is evidenced by the formation of small rounded voids or crevices within the metal and by surface blisters. The reaction that causes the blister is not an oxidation reaction, but rather the reaction of moisture or some other hydrogen-producing material with the aluminum surface at the solution heat treating temperature. This reaction produces atomic or nascent hydrogen, which then diffuses into the aluminum lattice. The atomic hydrogen then recombines to form molecular or gaseous hydrogen at discontinuities, such as grain boundaries or voids in the structure. If the gaseous hydrogen forms at a discontinuity near the surface and expands, a surface bubble occurs. The hydrogen can also collect at discontinuities below the surface, thereby causing subsurface voids or crevices within the metal, which are not visible on the surface. Subsurface HTO can only be observed by metallographic examination. Some examples of blisters and HTO occurring on a 2014 forging is shown in this illustration. The surface shows the bubble effect. When sectioned, the presence of the subsurface voids are evident, which is shown here. These subsurface voids can be structurally detrimental to the part and can only be detected by metallographic examination or ultrasonic inspection. The condition is aggravated by the presence of certain furnace atmosphere contaminants, especially sulfur, and by prolonged high-temperature exposure in a contaminated furnace environment. It may be alleviated by employing moisture-free atmospheres or volatile fluoride-containing salts. Moisture can be present due to the poor design of heat treat baskets and fixtures, which allow for entrapped water to be carried into the furnace with the parts. Allowing the furnace doors to stand open for extended periods of time over a hot quench tank can also result in moisture being carried into the furnace chamber. It has been found that even leaving furnace doors open for long periods of time on a humid day can result in problems, especially if there is sulfur present in the atmosphere. Sulfur can be carried into the furnace from a number of different sources. Sulfur-bearing lubricants left on parts after certain fabrication or forging operations is the most common source of sulfur contamination. Other causes of sulfur problems have been attributed to sulfur-containing materials which were present in tote boxes used to transport the material, to sulfur in the atmosphere from an oil refinery which was upwind from the heat treat plant, and to sulfur from the sulfur dioxide atmosphere which was used to heat treat magnesium parts. Prolonged high-temperature exposure itself does not cause blister problems. If the furnace atmosphere is properly controlled, parts may be left in furnaces for long periods of time with no damage. However, the random presence of moisture, sulfur, or both during a long soak period may blister a part at any time. Thus, some heat treaters, particularly in areas with atmosphere problems, pay special attention to minimizing soak times to preclude the possibility of HTO problems. To ensure that parts are heated and quenched properly, the correct racking of parts is essential. When racking parts for a solution heat treating operation, care must be taken to ensure that the parts are properly spaced so good airflow will allow the parts to reach the solution heat treating temperature evenly in the shortest period of time. An illustration of good racking practice is shown here. With the exception of extremely small parts, Excessive nesting, stacking, or part contact should be avoided whenever possible. Each part should have an adequate airspace between it and the adjacent part so that it will heat and quench evenly. Important consideration must also be given to the airflow of the particular furnace being used. Parts may be racked differently if the airflow is vertical or horizontal. Parts should be racked to allow for an even airflow over the entire load. Racking should not be done such that the first row of parts almost completely restricts the flow of hot air to other parts of the load. This practice can result in portions of the load not reaching proper solution heat treating temperatures. In one instance, one portion of a particular load of castings was found to be 100 degrees below the set temperature even after 12 hours of soaking at the solution heat treat temperature of 1,000 degrees due to airflow restriction caused by poor racking. When loading parts for salt bath operations, consideration should be given to the ease of part movement in and out of the salt bath. When racked parts are to be immersion quenched, consideration must be given to the ease of part movement in the quenching fluid so that the parts can be quenched rapidly and evenly to avoid distortion. One of the main causes of part distortion is poor racking practice. As we have observed in the previous discussion, at the solution heat treating temperature, the alloying elements are dissolved in the aluminum lattice, while at room temperature, they are located at grain boundaries or other large defect areas of the structure. If a part is slow cooled to room temperature from solution treating temperature, the atoms move within the lattice from their original dissolved location and congregate at defect locations, particularly near the grain boundaries, large voids or undissolved particles, where they will not have the opportunity of achieving a hardening effect. The atom moving process is a rate-dependent process in that it takes a specific amount of time to occur. The alloying atoms must actually travel or diffuse through the aluminum lattice to get to their final location. In order to achieve the higher strengths in the final heat-treated temper, the hardening elements must somehow be held in the solid solution at room temperature so that during subsequent thermal treatment, the hardness and the strength of the part will increase to the desired level. In other words, this atom movement must be retarded or stopped during the cooling cycle. Stopping this movement in order to retain the hardening elements in solid solution at room temperature is achieved through the quenching process. The quenching process is, for all practical purposes, a freezing process. The purpose of the quench is to hold or freeze the elements at their location found at the solution heat treating temperature. If the quench is sufficiently severe so that the parts are frozen instantly, the atoms do not have enough time to move. The severity of the quench necessary to achieve the required hardness or tensile properties depends on the type of alloy being heat treated and the thickness and configuration of the part. A schematic illustration of the microstructural changes that occur during the slow cooling and quenching processes is shown here. At the solution heat treating temperature, all of the alloying elements are dissolved in the aluminum structure. When viewed under a microscope, the only structure visible is a matrix with fine grain boundaries and a few small undissolved particles. When the material is slow cooled, the atoms diffuse to the grain boundaries and to other defect areas in the structure. No further changes will be noted when this structure is aged. If the solution heat-treated part is quenched, however, the structure after quenching is similar to that before the quench, as the alloying elements have been frozen in place. In this frozen state, the alloying elements are under a severe stress and do not like being trapped in their current location. In technical terms, this condition is called a non-equilibrium condition. These alloying elements, by themselves, even at room temperature, will start to move or diffuse to achieve an equilibrium condition. The movement of these atoms after the quench is called aging. During aging, the hardening elements move short distances and come out of solution or precipitate in local areas, resulting in significant strength increase in the part. The speed at which the atoms diffuse depends upon the temperature of the part and the type of material being heat treated. In some materials, such as precipitation hardening steels, the diffusion reaction is very sluggish. That is, the atoms move very slowly. Thus, the quench necessary to retard this diffusion and freeze the lattice need not be too severe. In aluminum alloys, however, this diffusion is extremely rapid. Therefore, an extremely rapid quench must be used in order to freeze the atoms in place. A rapid quenching medium, such as water or a water polymer solution, is normally used to quench aluminum alloys. The basic principles of quenching apply to other metals as well as aluminum alloys. During the quenching of any metal part, there are 3 stages of quenching which are illustrated on the cooling curve in the next illustration. These are the following. 1, the vapor blanket stage, the A phase. This is the first stage of cooling, which occurs just after a part is immersed in the quenching fluid. When an aluminum part at 1,000 degrees is quenched into a tank of water, the water that is in contact with the hot part instantly boils and quickly turns into a vapor. A vapor blanket or pocket then forms around the part due to the vaporization of the fluid as it contacts the hot surface. This vapor blanket formation is shown in the photo, which was taken by a high-speed camera during the quenching of a 1-inch by 1-inch aluminum alloy bar. Evidence has shown that there is a continual buildup and collapse of the vapor pocket as the hot liquid first contacts the surface of the heated part, is vaporized, and then backs away due to the formation of the vapor pocket. The entire process is repeated as fresh liquid again contacts the part, is vaporized, and forms a new blanket around the part. The process continues until there is sufficient agitation of the quenching fluid to keep fresh liquid contacting the hot part without forming the vapor pocket. During the A phase of quenching, the cooling rate of the part is extremely slow. 2, the vapor transport phase, the B phase. During the second stage of cooling, the vapor film has completely collapsed, and there is rapid heat transfer along with violent boiling as continual fresh, cool liquid contacts the surface of the part. During this B phase of cooling, actual quenching of the component takes place, and it is in this phase where control of the rate of quench for achieving properties is necessary. The quench rates obtained in the B phase of cooling are extremely rapid. 3, the liquid cooling stage, the C phase. In this phase of cooling, the surface of the metal temperature has been reduced to near boiling, so that no further boiling of the quenching fluid occurs. During this phase of cooling, the rate of heat extraction is again reduced to a level much slower than that measured in the B stage. This phase of quenching is sometimes termed the tail out. We have observed that the quenching operation is a freezing process, and that the purpose of the quench is to retain the hardening atoms in solid solution by retarding atom movement. Subsequent aging can then achieve the desired hardening reaction and required strength levels. We also observe that when a part is slow cooled, the atoms will diffuse and precipitate at the grain boundaries, thereby eliminating any possibility of hardening during the age. In order to effectively harden an aluminum alloy, then, it is necessary to ask the following questions. During the quench, are there some temperatures at which the diffusion reaction will occur faster than others? How fast must the parts be quenched, which we define as the critical quench rate, in order to effectively retard atom movement so that full properties will result? What happens at rates that are slower than this critical rate, but faster than an extremely slow cool? The first question is answered by the C curve in this illustration, which shows the property loss that occurs when an aluminum alloy is held at different temperatures during the cooling process. It shows that the temperature range of 750 to 550 degrees is most critical. When held at a temperature of 675 degrees, the high-strength alloys begin to lose properties in a very short time, less than 1 second. When the part was held for only 7 seconds at 675 degrees, the material lost 10% of the strength that would have been achieved by quenching directly. It should be noted that in holding both at a higher temperature, such as 800 degrees, or a lower temperature, such as 400 degrees, the property loss was not as large as at 675 degrees. From this study, it was demonstrated that the critical temperature range for quenching aluminum alloys is between 750 to 550 degrees. In this temperature range, the atoms diffuse and precipitate rapidly, and a resultant loss of tensile properties will occur. Thus, in the quenching process, it is important that the metal be rapidly quenched through this range to retard the diffusion and precipitation reaction. In order for the heat treater to properly select the procedures necessary to adequately quench an aluminum part through the critical range, one must have knowledge of 1, the critical cooling rate for each of the alloys to be processed, and 2, what effect quench rate slower than the critical rate will have on the resulting properties. With this information, the heat treater or specification engineer can select the appropriate quenchant and quenchant temperature to obtain an adequate quench rate for the parts in question. Because thick parts cool slower than thin parts, this information will also assist in determining the maximum thickness of aluminum that can be quenched in a particular quenchant. The answers to our questions, how fast must the parts be quenched, and what is the quench sensitivity for different alloys, are given in the following chart. To determine the quench sensitivity of different alloys, Alcoa quenched different alloys in various quenchants that produced different quenching rates. The resulting tensile strengths were then plotted against the measured quench rate through the 750 to 550 degree critical range, which was determined in the previous chart. As expected, slower cooling for all alloys resulted in lower properties. As the quench rate was increased, the tensile strength increased to a point where faster quenching did not appreciably result in any further increase in tensile properties. As we noted previously, this point is termed the critical quench rate. The critical quench rate is thus the rate above which faster cooling will not significantly increase the properties, but below which will cause a significant reduction in the properties. The level of properties achieved and the sensitivity of various aluminum alloys to different quench rates varies depending on the chemical composition and the working history of the part. As noted by the arrows in the illustration, the critical quench rate for 7178 alloy is extremely high, approximately 1,000 degrees per second, and its quench sensitivity very high, as noted by the rapid loss of tensile strength at quench rates below 500 degrees per second. Inadequate quenching of this alloy will result in much lower properties. From a practical standpoint, the quench sensitivity of an alloy is the controlling factor as to whether or not high properties can be obtained in thick pieces of aluminum. For example, due to the high quench sensitivity of 7178, it is impossible to fully harden the center of a 3-inch thick piece because a piece of that thickness cannot be quenched fast enough to retard the diffusion reaction in that alloy. On the other hand, alloy 6061 has a much lower critical quench rate than 7178, about 60 to 80 degrees per second. At that rate, 6061 will achieve full properties, and there is no need to quench it faster. Thus, for this alloy, thin sheet products will fully harden using slower quenchants, and it's much easier to achieve full hardness in thicker pieces. This is why spray quenching is sometimes used on 6061 alloys, but rarely, if ever, on 7075 and 2024. Each alloy has its own critical quench rate and degree of quench sensitivity. The most common quenchant used for aluminum alloys is water. The main advantage of using a water quenchant is that water can provide the rapid quenching speeds necessary for achieving high properties in many different alloys. Water is also cheap and readily available. In addition, water is somewhat flexible in that its quenching characteristics can be changed by varying the water temperature. The use of ambient or room temperature water, commonly termed cold water quenching, is the most common practice for quenching aluminum alloys. The water tank is usually controlled over the temperature range from 50 to 90 degrees. Most government and company specifications require that the temperature of the water bath be below 90 degrees at the start of the quench and not raise more than 10 degrees after the quench. Most product forms such as sheet, plate, extrusions, and some forgings are quenched in cold water. The major problems of water quenching are twofold. First, many parts will warp or distort during the quenching process. And second, thicker parts can achieve a high level of residual stress, especially by cold water quenching. The problem of quenching distortion or warpage has been one of the major problems facing the aluminum heat treater for decades now. Many approaches have been used, each with varying degrees of success and each with its own limitations. In an attempt to achieve, first, maximum distortion control in thin sheet metal parts, and secondly, minimum residual stresses in forgings and castings, hot water quenching is sometimes used with moderate success. Temperatures used are from 140 degrees to boiling. The quenching characteristics of a water quench tank are significantly changed by heating the water. To illustrate this fact, a property loss curve for 7075 alloy is shown here. It can be seen that as the temperature of the water is increased, the quenching characteristics of the bath are slowed significantly. A significant loss in tensile properties resulted when the water temperature was raised above 160 degrees, as the cooling is not sufficient to freeze in the solute atoms during the quench. An 82,000 pounds per square inch tensile strength was achieved in cold water, while the strength dropped to 64,000 psi when boiling water was used, a loss of 25%. Even high-strength castings can lose properties if the quench water temperature is too high, as shown here. Because of the rapid change in the quenching characteristics of water above 160 degrees, control of quenching speeds at various locations in a quench tank is difficult when using a hot water quench. Different quenching speeds can be found at different locations within a given tank, in different tanks, and in sequential loads in the same tank due to both differences in temperature and slight differences in agitation rates. Thus, precise quenching control is difficult to achieve when using hot water in production quenching operations. We have seen that water is the most used quenchant for aluminum alloys. Water, although an inexpensive, universal, rapid quenchant, is too severe a quench for many applications and can cause excessive distortion, high stresses, and in certain instances, quench cracking. By varying the water temperature, some flexibility is achieved in quenching characteristics. Many of these quenchants and methods have been used in production applications. The most common of these are the spray or fog quenching and the use of polymer or glycol quenchants. Some distortion problems can be solved by using spray quenching techniques. The commercial application of spray techniques in aluminum alloys varies from the use of a heavy volume of a high-pressure spray to that of a light fog or mist. Thus, the quenching characteristics of a particular spray quench facility can vary significantly depending upon the design and characteristics of the equipment being used. When using spray quenching techniques, care must be taken to ensure that the procedure is adequate for achieving the required properties in all parts being heat treated. The use of spray quenching normally results in much lower quench rates when compared to cold water immersion quenching. As a result, spray quenching can result in a significant loss in tensile properties when the part is later aged, especially when heat treating the more quench-sensitive 2000 and 7000 series alloys. This property loss can be particularly high if the temperature of the water spray is raised above 160 degrees. If spray quenching is considered for aluminum heat treatment, a careful study should be made involving the thickness of the part, the alloy being heat treated, its quench sensitivity, and the shape or configuration of the part to ensure that the quenching is adequate and that a degradation of properties will not occur. Pre-production qualification of the quenching procedure, including both destructive and non-destructive testing of heat-treated parts, should be performed before a spray technique is used. Once the technique is established, it must be rigidly followed regarding racking, placement of nozzles, and pressure of the spray. Also, rigid maintenance procedures must be followed to ensure that nozzles do not get plugged or corroded. Most higher strength, highly quench-sensitive alloys, such as 7075 and 2024, are not spray quenched, except in special circumstances, because slower quenching can result not only in lower properties, but also a significant reduction in intergranular corrosion resistance. If a spray quench is used on these alloys, it must be a heavy volume spray, which floods the part rapidly, and it must extract a large amount of heat quickly. A light fog or mist spray or quenching with a handheld hose is not adequate for quench-sensitive alloys and for the thicker parts of even the less quench-sensitive alloys. One of the major problems of spray quenching is assuring that all of the parts of the load are effectively flushed by the spray. Sometimes a heat treater will load parts in such a manner that those in the center of the load are not effectively quenched because they are obstructed from the spray by other parts on the load perimeter. Care must be taken to ensure that all of the parts of the load are effectively flushed by the spray. Applications of polymer quenching techniques to aluminum alloy heat treatment has allowed the heat treater to achieve more consistent results when attempting to solve quenching-related problems. The two main advantages of using polymer quenchants are, one, the control of distortion, particularly in thin sheet metal products, and two, the reduction of residual stresses in the quenching of larger parts, such as forgings and castings. The polymers allow for precise control over quenching speeds, which is not achievable through the use of hot water. Polymer quenchants have found wide application for most aluminum products, such as sheet material, extrusions, forgings, castings, and especially fabricated parts which have been machined and/or formed. The most accepted of the available polymer quenchants is the Type 1 polyalkylene glycol-based quenchant, which is specified in the SAE specification AMS 3025. The speed of the polymer quench is controlled by varying the concentration of the polymer. Heating the tank is not necessary. The higher the concentration of the polymer, which is water-soluble, the slower the cooling rate. Slight temperature changes in the tank do not significantly affect the cooling rate. Thus, the problem of obtaining different quench rates due to the temperature variation, which commonly occurs in a hot water tank, is not a factor. The variation of the cooling characteristics is best illustrated by the review of the cooling curves for materials of different thicknesses. This illustration shows a series of curves for 1/2 inch 7075 aluminum alloy plates at different concentrations of a Type 1 polymer. It can be seen that the quenching characteristics vary significantly by simply changing the concentration of the polymer. Coupled with alloy quench sensitivity data, the heat treater can use this data to select a concentration that will provide him the proper quenching speed to achieve required properties in a specified part. When polymer quenching parts to military requirements, the concentrations of the polymers used are outlined in SAE specification AMS 2770, heat treatment of aluminum alloy parts. The requirements of selected alloys and forms are shown here. With the exception of thin sheet metal parts, it is recommended that the quench tank be vigorously agitated for most water tank quenching operations. Agitation is usually achieved by moving the liquid, either by a pump or an impeller. The use of air agitation for aluminum quenching is a controversial subject and is prohibited by some specifications. Air agitation is sometimes used in cold water tanks, but care should be exercised in using air, especially when quenching in hot or boiling water. Excessive air-entrapped bubble formation, particularly in the vicinity of thick parts, can result in soft parts or soft spots due to inadequate surface contact of the fluid with the hot part during the quench. Air agitation should not be used in boiling water or polymer quenching. When doubt exists as to the effectiveness of a particular agitation method, tests should be made to ensure that the technique is adequate for achieving a satisfactory quench on the thickest piece of the most quench-sensitive alloy being processed. We have previously observed that when heat-treating aluminum alloys, the quench is used to freeze the hardening elements in their solid solution location so that with further processing, the material will increase in strength and hardness to a desired level. Immediately after the quench, a heat-treatable aluminum alloy is very soft and ductile and possesses low tensile properties. The hardening atoms, which are dissolved in solid solution within the lattice, are in an unstable condition. With time, these dissolved elements will move or diffuse to a more stable location, where they will congregate and come out of or precipitate from solid solution and cause a hardening reaction. This diffusion and precipitation process is called the aging process because it occurs over a period of time, from hours to years. When performed at the proper time and temperature, the aging process will cause a 3 to 5-fold increase in the yield strength of an as-quenched aluminum part. The aging reaction can be performed either at room temperature or at some elevated temperature between 225 to 450 degrees. If the aging is performed at room temperature, the process is said to occur naturally and thus is termed natural aging. If the material is heated to an elevated temperature in an oven or furnace, the process is termed artificial aging. The strength, hardness, and ductility properties achieved by the aging process can vary significantly depending upon the times and temperatures used. When aluminum alloys are naturally aged at room temperature, a gradual increase in the tensile properties occurs as aging progresses with time. The rate of increase and the final properties achieved vary with each alloy. The illustration shows the increase in tensile and yield strength as two more common heat-treatable alloys, 7075 and 2024, are naturally aged. It can be seen that the natural aging response for a 2024 alloy is completely different than for a 7075 alloy. For both alloys, the tensile strength increases steadily with time for the first 100 hours. After 100 hours, no further change occurs in the 2024 alloy with increased aging. Thus, the strength level for this alloy reaches its maximum in about 4 days, and a usable temper is developed, as the properties do not change significantly thereafter in service. As the material has become stable, a designer can accurately predict how it will perform in operation. The T3 and T4 tempers are the tempers achieved by natural aging aluminum alloys to a stable condition in about 4 days after quenching. These naturally aged tempers are widely used for many aluminum alloys, particularly of the 2000 and 6000 series. In contrast to the ability of the 2024 alloy to achieve a stable, naturally aged condition, the 7075 alloy never achieves stability with room temperature aging. The natural aging reaction, which is caused by the precipitation of complex precipitates, continues to progress indefinitely, so that even after 100,000 hours, or 11.4 years, the alloy is still continuing to increase its strength level. Thus, a designer cannot effectively predict the exact performance of a T4 type 7000 series alloy in service because its properties are constantly changing with time. The ability of some alloys to achieve stability with a natural age explains the widespread use of the naturally aged T3 or T4 tempers for alloys such as 2014, 2024, 2219, and so on. The inability of many alloys, particularly most of the 7000 series alloys, such as 7075 and 7050, to achieve stability with a natural age, explains why they are not used in the T4 temper, and why T3 or T4 tempers do not exist for these alloys in the literature. The room temperature aging rate can be significantly retarded if a part is chilled immediately after quenching. The change of the yield strength versus aging times at room temperature, 32 degrees and 0 degrees, is shown for alloy 7075 in this next figure. It should be noted that these curves are plotted on a log time scale, and thus the temperature effect is more significant than it might first appear. At room temperature, the alloy starts to age about 1/2 hour after the quench. If the temperature of the quenched part is lowered to 0 degrees, aging is retarded so that a strength increase does not begin to occur until approximately 1,000 hours has elapsed. Fabrication operations such as forming or check and straightening are frequently performed on heat-treated aluminum alloys after solution heat treating and quenching. Most aluminum alloy parts undergo a check and straightening operation to correct distortion or warpage problems that have occurred during quenching or prior fabrication operations. Also, some parts are intentionally formed in the as-quenched condition and then aged to produce a finished part. The ability to successfully retard the natural aging reaction of heat-treatable aluminum alloys by refrigeration has a significant impact when considering the forming operations after solution heat treating. Immediately after quenching, the material has a low yield strength, is soft and pliable, and is readily formable because the yielding needed to achieve a permanent set while forming can be easily obtained. If the check and straighten or forming procedure is delayed for any reason and the material is allowed to naturally age at room temperature, the operation becomes more difficult because greater force is required to exceed the ever-increasing yield strength caused by the natural aging process. Thus, inconsistent forming and greater springback conditions usually occur if fabrication is delayed at room temperature for too long a period after the quench. Any forming operation required after quenching, such as stretching, drawing, breaking, and so forth, is much easier to perform in the as-quenched condition when the yield strength is at its lowest level. Refrigeration is usually necessary because the level of springback encountered will change as the part naturally ages. In order for the operator to establish constant forming parameters, such as degree of stretch, forming limits, and so on, the material being formed must be stable. Variations in strength from lot to lot or from one end of the run to the other, resulting from the natural aging process, can cause significant forming problems. In some instances, the material can age sufficiently to even preclude the use of existing forming equipment, as the loads required to achieve a permanent set may exceed the capacity of the equipment. Effective refrigeration will keep the material soft and easily formable and will aid in achieving consistent results. For most high-strength alloys, the highest strength, maximum stability, and optimum corrosion resistance are achieved by artificial aging. In the artificial aging procedure, the material is heated for the required length of time at some elevated temperature, usually from 225 to 440 degrees. The time will vary depending upon the temperature required, the temperature selected, and the properties desired. The strength increase achieved by artificial aging of most high-strength aluminum alloys is significant and can be as great as 4 times greater than the as-quenched strength. The diffusion and precipitation reactions which occur during artificial aging are complex. In many instances, hardening is achieved by the precipitation of many different particles, which precipitate at different rates, at different temperatures. Care must be taken so that the parts are aged at the correct times and temperatures so that aging occurs properly. The normal temperature tolerance for artificial aging of aluminum alloys is plus or minus 10 degrees. Most good heat treaters specify plus or minus 5 degrees in their aging practice. To achieve the desired combination of mechanical properties, ductility, corrosion resistance, fracture toughness, etc., parts may be peak-aged, under-aged, or over-aged. Let's discuss the time-temperature relationships that govern the artificial aging of aluminum alloys. At any given temperature, the artificial aging reaction progresses with time, and the strength level increases until it reaches a maximum or peak value. Further aging beyond this peak value results in a reversal in the property trend, causing a reduction in the alloy's strength and hardness. Terminating an age before the peak strength value has been achieved is called underaging. Aging beyond the peak value is called overaging. A typical series of aging curves, in this case for 6061 alloy, is shown in this illustration. Artificial aging is temperature dependent. The higher the temperature, the faster the aging reaction progresses. However, as a general rule, higher strengths are eventually achieved when lower aging temperatures are used. This effect is illustrated in this figure, which shows the effect on the yield strength when alloy 7075 is artificially aged at 3 different temperatures. At the highest temperature noted, 300 degrees, aging occurs very rapidly, and the maximum yield strength is achieved in about 8 hours. At lower temperatures, the aging reaction progresses more slowly, and it takes much longer to reach maximum strength. At 275 degrees, it takes from 36 to 48 hours for this alloy to reach its maximum yield strength. At 250 degrees, the yield strength has not reached its maximum value after 36 hours of furnace exposure. The maximum yield strengths which are reached for the different aging temperatures are shown in this table. It can be seen that aging for longer times at a lower temperature usually will result in higher tensile and yield strengths. To obtain the highest possible strength for a specific alloy, an aging temperature is selected that will achieve the highest possible properties within a reasonable length of time. At higher temperatures, aging can be accomplished in a shorter length of time, but at some sacrifice in tensile properties. At lower temperatures, higher ultimate strengths are achieved, but longer exposure cycles are required. Many alloys are not aged to achieve the highest strengths because other factors are important in the operation of the part. The most important classifications in this area are the corrosion and stress corrosion cracking resistance of many aluminum alloys. In the aerospace industry, there are many parts which are made from the 7000 series alloys, which are heat treated to the T6 condition. However, it has been found that at peak strength levels, many aluminum alloys are highly susceptible to service failures from corrosion and stress corrosion phenomena. Some 7000 T6 or T6X product forms, such as forgings and thick plate, have been found to be extremely susceptible to problems of environmental stress cracking, such as stress corrosion cracking and exfoliation corrosion. Experience with critical components such as landing gears, hydraulic cylinders, and wing and fuselage spars has shown that the T6 type tempers of these alloys are not acceptable for long-term service in many critical applications. In service, a part aged to the T6 temper may satisfactorily carry the required ultimate load for a short duration. However, if the same part is exposed to a mild corrosive environment and either contains a high level of residual stress or is subjected to a continuous load, premature failure can result. Thus, in order to make these materials more usable, it is necessary to overage them to lower strength levels in order to achieve better resistance to corrosive environments. The widespread use of tempers like the T73, T74, and T76 for most 7000 series alloys are good examples of this practice. A typical stress corrosion crack that occurred in a 2024 T6 part is shown in this photo. Instances have been reported of new T6 parts failing overnight while just laying on the shelf before ever being placed into service. In recent years, two-step overaging has become common practice for heat treating many aluminum alloys. In this procedure, the material is first aged at a lower temperature, such as 200 to 250 degrees for some period, usually anywhere from 6 to 24 hours. The alloy is then given a second and sometimes even a third age at a higher temperature, usually 300 to 375 degrees. The practice of two-step aging was first introduced in the 1950s in order to reduce the total furnace time required for some T6 aging practices, particularly those of the 7000 series alloys, which often required 24 to 48 hours of furnace time to obtain desired properties. More recently, step aging has been used to achieve the overaged T7 tempers, such as T73, T74, and T76 of the 7000 series alloys, such as 7075, 7049, and 7050. The step-aged T7X tempers were developed to solve stress cracking problems. It was found that the step age was necessary to obtain high tensile properties for carrying maximum loads, while at the same time making the parts resistant to problems involving stress corrosion cracking and exfoliation corrosion. It was also found that in some instances, the step age also improved other properties, such as fracture toughness. The need for using a multi-step age is sometimes subtle and not readily apparent to many heat treaters. As a result, the necessity for employing two furnace operations is not fully understood. This confusion stems from the fact that often similar inspectable properties, like hardness, strength, and electrical conductivity, can often be achieved by a single-step process using the higher temperatures. Sometimes heat treaters will purposely eliminate the first step of the aging treatment to save time and energy without realizing the damage they may have done to the parts by eliminating the two-step process. Let's now discuss the annealing and stress-relieving processes. The purpose of annealing is to soften the alloys and to relieve stresses that were imparted by prior forming operations so that subsequent forming operations can be performed. The purpose of stress relieving is to relieve residual stresses that have been imparted in prior fabrication or heat processing operations. All annealing of aluminum alloys is performed by a thermal process. Stress relieving, to relieve quenching stresses, is accomplished mostly by a mechanical process, such as stretching or compressing the material immediately after the quench. These processes are normally performed only at primary mills. Stress relieving is also accomplished by thermomechanical means, also called uphill quenching, which involves the use of cryogenic temperatures followed by a thermal shock treatment, usually with live steam. There are three different types of thermal annealing and stress relieving practices used for aluminum alloys. These are first, the full anneal; second, the stress relieve anneal; and third, the low temperature stress relief. Full annealing is used to obtain the softest possible condition to allow for further forming operations. Full annealing eliminates all prior conditions. It is often used to homogenize cast structures. Full annealing aluminum alloys is accomplished by heating the material to 775 degrees, holding for 1.5 to 2 hours, and then furnace cooling slowly, typically at 25 degrees per hour, down to room temperature. The 775 degrees is high enough to dissolve some of the hardening elements into solution. By slow cooling down to room temperature, the hardening solutes that went into solution diffuse and precipitate out of solution as the part cools. This procedure results in maximum softness. After the 775-degree furnace treatment, if the material is cooled too fast, the material may be fairly soft initially at room temperature. However, if it is let to sit at room temperature for a period of time, its strength will increase. This strength increase may seriously affect the formability of the part for the next forming operation. The stress relief anneal is used to eliminate the strain hardening effects of cold working the material in forming operations, such as deep drawing, bending, and spinning. A soft material can only be work hardened to a certain limit. Further work will cause cracking and fracture of the part. A stress relief anneal is usually performed by heating the material to 650 degrees and holding for 1.5 to 2 hours, and then air cooling. The 650-degree temperature is high enough to stress relieve the cold-worked grains, so they transform into stress-free grains. This temperature is not high enough to dissolve significant amounts of hardening solutes into solution, so the air cool is adequate to achieve a significant softening and stress-relieving effect. Let's now review low-temperature stress-relieving operations. Effective stress relieving of aluminum alloys is only accomplished at temperatures usually above 425 degrees. This is due to the fact that in order to thermally reduce residual stresses that are generated by forming or welding operations, the yield strength of the material must be reduced. Unfortunately, in order to significantly reduce the yield strength of aluminum alloys by raising the temperature must be raised above 425 degrees. And unfortunately, most aluminum alloys are aged at temperatures below 425. Thus, stress relieving at higher temperatures will seriously lower the properties. In spite of this problem, many companies use low-temperature stress relieving of age-hardened alloys to reduce residual stresses from forming, straightening, or machining operations. Although a truly effective full stress relief is not obtained by this practice, some stresses will be relieved and may place the part in a more acceptable condition for service use. Usually, when using a low-temperature stress relief, the practice is to stress relieve at a temperature which is 25 to 50 degrees below the final age temperature for a period of 1 hour. This practice will not usually reduce the strength of the part. However, when reheating an aged aluminum part, proper quality control tests should be performed to ensure that the part has not been damaged. Aluminum alloys are heat treated for the purpose of achieving a desired characteristic or property, which will enable a part to successfully perform its designated function. The most common design requirements that the aluminum heat treater must meet are strength and resistance to stress corrosion cracking. Other material properties such as fracture toughness, hardness, ductility, and dimensional stability are critical in many instances. The ultimate responsibility for verifying that a heat-treated part meets all requirements is the function of an intricate quality control system. Quality control or inspection personnel are normally assigned the responsibility of verifying that the material possesses the desired characteristics so that the part may be placed in service. The quality control system used in aluminum heat treat plants involves the proper certification of furnaces, instrumentation, and other equipment, and the inspection testing of parts or accompanying test material. The testing may be either direct or indirect. The only completely reliable method for verifying that a certain property has been achieved in the manufacturing and heat treating process is to directly test for the desired property. If a part is to meet a specific tensile or yield strength, A sample would be taken from the part and tensile tested. The same would be true for stress corrosion testing. This approach is destructive and costly, particularly when many companies may be involved in producing the final product. The inspection tests used in the aluminum heat treat plant normally involve 5 of the most common tests: hardness testing, conductivity testing, tensile testing of actual parts or accompanying test material, fracture toughness testing of accompanying material, and stress corrosion testing. Heat treatment of aluminum alloys at primary metal producers, including mills, foundries, and forge plants, normally requires some level of direct testing, such as tensile testing, with every load. Also, in some instances, fracture toughness and stress corrosion tests will be performed. The necessity to perform these tests is usually determined by the drawing requirement or the government or industry specification to which the material is purchased. However, it is not feasible for every heat treater to always use direct verification tests to determine that each part or lot of parts meets all specification requirements. For example, a part may be subjected to high tensile loads or may undergo a certain fatigue load while in service. It is not practical for the in-house or commercial heat treater to test every part or lot for fatigue or tensile properties. Some direct testing, such as tensile, fracture toughness, or stress corrosion testing, is required in extremely critical situations. The commercial heat treater, in most instances, uses a series of indirect tests, which involve mostly hardness and electrical conductivity measurements to verify that parts being heat treated have been processed correctly. These tests are usually supplemented by additional tests, such as periodic tensile tests and tensile tests conducted on control specimens which accompany critical materials. The indirect methods currently employed are non-destructive tests, such as hardness and electrical conductivity, which are easily performed. Prior to using an indirect test, data involving the correlation between different engineering properties, including some statistical analysis, must be available. Also, the quality system must cover some form of lot control and a comprehensive certification system, all for the purpose of ensuring that the results of the indirect testing will reliably indicate that the final parts will perform satisfactorily. Heat-treated aluminum alloys respond to hardness changes in an entirely different manner than do steels. The aluminum hardening reaction is a precipitation reaction, not a martensitic reaction. As a result, the use of hardness measurements, tensile tests, and their relative correlations must be given closer scrutiny and used with extreme care in predicting the usefulness of a heat-treated aluminum alloy part. In most instances, a particular part will function successfully if it possesses adequate strength characteristics. Thus, the tensile test, which provides the material's yield strength, tensile strength, and the level of ductility, as measured by percent elongation, is most useful. For heat-treated aluminum alloys, this test is almost always performed by the producer of the material to verify that the heat-treated alloy does or will meet the required property level when properly heat-treated. Usually a test part, or in some instances, separately forged or cast test samples, which accurately represent the parts being processed, accompany the parts through the processing sequence and are then tensile tested for verification. The hardness values of aluminum alloys are extremely dependent upon both the chemical composition and the processing history, as well as the heat treat processing sequence. Different aluminum parts possessing the same hardness values can exhibit widely different strength levels. Although there is a general correlation between the hardness and the strength of a particular heat-treated aluminum alloy, one cannot absolutely predict the strength or corrosion properties from hardness values alone. Hardness measurements are extremely valuable for indicating that an alloy has been processed correctly and that a desirable strength has been achieved. For absolute verification, actual tensile tests must be performed. However, indirect testing, using a combination of hardness and electrical conductivity tests, which are supported by adequate processing records, process control tensile tests, and reliable certifications, can be effectively used in an acceptable quality system for achieving full confidence. Electrical conductivity testing is one of the most commonly used tests in the aluminum heat treating plant. All metals are conductive in that they have the ability to carry electricity. Each type of metal, such as steel, copper, aluminum, and titanium, has a different resistance to the current that is being carried. Some aluminum alloys, particularly those that contain copper, as do the 2000 and 7000 series alloys, are unique when compared to other metals. For these two alloy classes, the resistance and the resulting ability to carry current has been found to significantly change with the heat-treated condition of the alloy. This is not true with other metals, such as the steel and titanium alloys. When performing an electrical conductivity test, the conductivity is measured in percent IACS, which means percent of the International Annealed Copper Standard. As pure copper has one of the highest current carrying abilities, it is used as a standard against which to compare other metals. The number represents a percentage of the electrical conductivity carrying capacity which would be achieved by a pure copper bar which has been annealed. In the 1960s, the aerospace community was faced with a serious problem of stress corrosion cracking of many alloys heat-treated to the T6 temper. As a result, the overaged T7 tempers were developed to provide structural components that had increased immunity to stress corrosion cracking. Up until that time, the hardness test had been used as the only non-destructive test to determine if an aluminum part had been heat-treated properly. However, it was found that the hardness test was not adequate to positively distinguish between a 7000 alloy that had been aged to the T6 temper from one that had been aged to a T73 temper. Although the overaging did result in a reduction in hardness from the T6 condition, the T6 temper generally resulted in Rockwell B hardness readings from 83 to 93, while the T7 temper showed values of 78 to 88. Thus, an overlap occurred in the range of Rockwell B 83 to 88, so that materials heat-treated to a T6 or T73 temper could both show hardness readings in that range. So, if a heat-treated part would have a Rockwell reading of 85, the aerospace inspector would have no way of telling from the hardness reading alone if the material were T6 or T73. The hardness test was therefore not sensitive enough to positively discriminate and verify that the part had been overaged to a T7 temper and would be resistant to stress corrosion cracking problems. Another method was needed. The electrical conductivity test solved this problem. Conductivity testing was developed as a non-destructive method to distinguish aluminum alloys which had been overaged to achieve a T7 temper from those that had been aged to the T6 temper. The electrical conductivity tests for 7000 series aluminum alloys in a T6 temper usually are in the range of 32.5 to 35.5% IACS. When the material is properly overaged to the T7 temper to achieve stress corrosion resistance, the conductivity increased approximately 6 points, so that the final conductivity was approximately 38 to 42% IACS. The conductivity meter became a valuable tool in the plant, for it could non-destructively verify that a material had been properly overaged. When first used, conductive testing was only used for this purpose. It soon became evident, however, that the conductivity test had applications beyond its original intended use. It was found that other alloys, such as many 2000 series alloys, showed similar electrical conductivity characteristics as a function of heat treatment. Other applications have proved valuable. The conductivity test can also be used to determine the effectiveness of a quench, and in some instances, determine if an aluminum alloy has been properly annealed. An illustration of this is shown in the next table, which shows electrical conductivities achieved for a 70-75 alloy for different tempers. The conductivity test became the most widely used non-destructive test in the aluminum heat treat plant. It is used both instead of and in conjunction with hardness testing to verify the adequacy of processing. In the aerospace community, conductivity testing is required on all 7000 series aluminum alloys, which are heat treated to either a T6XX or T7XX type temper. It is also used on many other alloys to verify heat treat response. The conductivity test is covered in SAE AMS 2759, Electrical Conductivity Testing of Aluminum Alloys. One must be careful when using the test or interpreting data on certain alloys. The change in electrical conductivity experienced by some aluminum alloys is not apparent in others. Many alloys, particularly those that do not contain an appreciable level of copper, such as the 6000 series and many casting alloys, do not show sufficient variation in electrical conductivity to use the test as a positive indication of heat treat response. In these cases, it is absolutely imperative that supporting hardness tests be used for acceptance decisions. Also, two aluminum parts which show similar conductivity readings for the same alloy can show a significant difference in hardness and tensile properties. Tensile property, hardness, and electrical conductivity relationships of aluminum alloys are extremely dependent on the chemistry of the alloy and the working history of the product. Controlling the temperature distribution of a furnace or oven used for solution heat treating and aging aluminum alloys is one of the most critical operations in the plant. Precise temperature control is necessary. Low properties and even permanent damage can be done to parts if the temperature is not adequately controlled. Aluminum solution heat treating furnaces and aging ovens can be very large, and the temperature of the entire work zone must be controlled to as close to plus or minus 5 degrees as possible. The heat treater must have complete assurance that the temperature variation within the whole furnace working zone is maintained within the temperature tolerance required, with no overshoot allowed. In a solution heat treat furnace, even a slight variation of as little as 10 degrees can cause eutectic melting of the alloy and permanent damage. If the temperature is too low, lower than acceptable mechanical properties will result. Thus, the furnace must be designed so that the uniformity of the temperature throughout the whole work zone is maintained by controlling just one thermocouple. This necessitates careful selection and adjustment of proportioning type control instrumentation. This control is achieved in the furnace design by proper sizing and location of the heating elements and proper sizing of the fan and furnace baffle system to ensure proper airflow. The ability of a new furnace or oven to maintain proper temperature distribution is the responsibility of the furnace designer and the manufacturer. The assurance that the furnace continues to provide adequate temperature control and distribution is the final responsibility of the heat treater's quality assurance department. The heat treater must be aware of the condition of the furnace to successfully heat treat parts on a daily basis. The temperature distribution of the work zone must be surveyed initially on a new furnace and checked periodically thereafter, usually at a minimum of a monthly basis. The temperature survey must also be conducted after any change or modification in the furnace that could affect the temperature performance. The survey involves placing numerous thermocouples on a rack, which represents the furnace work zone, and loading the rack into a pre-stabilized furnace. The thermocouples are then read for a period of time, usually 30 minutes to 1 hour, to ensure that the furnace maintains the proper temperature tolerance throughout the work zone. Readings are taken usually at either 2 or 5 minute intervals during the furnace recovery and soaking period. A complete history of the survey record should be recorded and filed. A typical survey distribution shows the temperature of the individual thermocouples during the recovery period of the load to temperature and during the soaking period of all the thermocouples in the working zone. Most companies build special permanently mounted thermocouple racks with as little as 9 and as many as 60 thermocouples located throughout the work zone for this survey test. When checking thermocouple surveys, 3 critical items must be examined. 1, that no overshoot occurs as the temperature approaches the required temperature range. 2, that all reading thermocouples are within the required temperature tolerance. And 3, that there is no trend toward a temperature rising for longer soak periods after the initial 30-minute survey is finished. In certain instances, it is imperative that the survey be conducted for a longer period of time if the thermocouples, at the end of the normal 30-minute time frame, are still increasing in temperature, because in long temperature soaks, such as 4 or 5 hours, the temperature could settle out at a temperature which could be 5 to 10 degrees higher than that which is indicated in a short-ended survey. One of the most critical operations in the aluminum heat treating plant is that of the radiation survey. As aluminum heat treating furnaces or parts are heated through convection and conduction heating, radiation heat in the aluminum furnace must not be a factor. All aluminum parts in an aluminum solution heat treating furnace should only be heated by convection, by the hot air moving past the part. The part should not be heated by the radiation from the sidewall of the furnace. Experience has shown, however, that aluminum heat treating furnaces, particularly in the range of 800 to 1000 degrees, can sometimes, if designed improperly, cause a problem whereby the radiation from the sidewalls of the furnace can cause overheating. This condition has been known to cause serious problems of overheating and eutectic melting in structural components. Often this condition is not detected through inspection procedures. Thus, the heat treater must have complete assurance that the solution heat treating furnace has no radiation heating problems. Problems of radiation heat treating usually come from an improper furnace design or damage to the furnace which has not been corrected by proper maintenance procedures. The radiation survey is usually accomplished by placing panels on a rack at the extremities of the work zone and attaching a thermocouple to each panel. The panels usually measure 1 foot square and are approximately 1/8 of an inch thick. A minimum of 9 panels are surveyed on each side, facing a wall which has heating elements in the side wall of the furnace. The survey is conducted by loading the rack into the furnace and measuring the temperature of the panels as the furnace recovers and progresses through a simulated soak period. The temperature measurement of the panels will show any evidence of radiation heating from the sidewall. Experience has shown that in cases of improper furnace design or inadequate furnace maintenance, that sidewall radiation heating has caused parts to overheat as much as 50 degrees, even though the control thermocouple was still measuring the correct set temperature. The parts adjacent to the sidewalls of the furnace experienced radiation heating, which resulted in eutectic melting. Parts in the center of the load were unaffected. The radiation furnace survey should be conducted in every new furnace installed in a heat treating plant. This will indicate whether or not the furnace has a radiation heating problem. Any significant maintenance on the furnace, such as the changing of heating elements or radiant tubes, the change or redesign of the furnace retort or chamber, or maintenance or repair of the airflow system and or chamber, necessitate that a radiation survey be reconducted. It is essential that proper radiation and air surveys be conducted on furnaces performing aluminum heat treating operations. Any furnace problem must be quickly corrected with proper maintenance and the furnace resurveyed. Only with this type of plant control can the furnace operator and quality control personnel be assured that parts are not being overheated and damaged.